Okay, then let's go to the real stuff, right? We spent 2 classes to to learn about what quantum computers are about. They are very superficial, but they contain the key words, the key concept. But now we really need to make our hand dirty, right? And as I've been emphasizing to many students, I don't care. It doesn't matter you are undergraduate physics or EE or any other major. I will start from scratch. For some of you, maybe you think it's too easy, but not really. Just think about that. Try to rethink from another perspective. It's not really that easy. So we'll start with the linear algebra, right? So let's talk about vector space and basis. This one you understand very well, right? Let's start with something really simple. So we have a 2D coordinate, yeah? And this is x direction, this is y direction, we know very well. And we know that we put 1, 2, 3, 4 here. And we also put 1, 2, 3, 4 here. And you know very well, 1, 2, 3, 4 on the x-axis means I have 1 unit or 1 part of x hat, 2 parts of x hat, 4 parts of x hat, 3 parts of x hat, etc. Right? And of course, let's say I have a vector, right? This vector is like this. It goes from here to here, right? This vector, I call it V. So how do we represent V, right? You can say it out also, right? V equal to what in terms of x hat and y hat? Say again. Thank you. 3x hat plus 2y hat. This is something you may think very easy, right? But what is x hat, y hat? We never thought about that. So it's the basis state, right? Of course, now you feel that just this unit is x hat. But remember, this is the basis. It's just like I say H2O, water. A water molecule is formed by 2 hydrogen molecules and 1 oxygen molecule. I can even say that, okay, the hydrogen atom is basis. Oxygen atom is basis. So I have 2H and 1O. And what is hydrogen? I don't know. Let's say I'm still in the ancient time. I don't know. Right? So ancient time, they even say that everything formed by fire, earth, wood, and metal, if I'm right. So maybe the whole world only have 4 bases. But what is fire? What is wood? What is metal? Actually, you don't know, but we take it for granted, right? So that is the basis. So now we represent a vector. We say, okay, it has 3 units of x hat and 2 units of y hat. And don't worry about that. We will just say, okay, we agree. Maybe that is correct. I don't care what's x hat and y hat. And you know that we can also write it as 3, 2 in column form. If you forgot about this, doesn't matter, then relearn it. Now I tell you that I can write the vector as 3 and 2. Now when I write this, we need to agree with each other what we are talking about. We're talking about that the first row means I have 3 units of x hat. The second row, I have 2 units of y hat. Okay, as long as we agree with each other, I just like 3 and 2 is enough. I don't need to say 3x hat plus 2y hat. Agree? Okay, so if this is the case, why I need to follow the tradition? If I say that there's something called x cat, 3x cat plus 2y cat, K-E-T, right? We have not learned this yet, but I write it in this way. Would that be a problem, except that you never seen that before? Am I making any technical mistake? Or you think that I'm lousy in the definition? You think about that? No, right? Because to be frank, you also don't know what is the meaning of x hat. You bring this to the kindergartner, they know how to count. You say x hat. They won't feel that x hat is more normal than cat x, right? For a kindergartner, right? So I can write it in this way, right? So to be more extreme, I actually can say that 3 happy face plus 2 sad face. If I want, as long as you and me agree what it means, right? So here we just want to emphasize X hat and Y hat are the so-called basis state, right? So you know all this, but we try to emphasize the meaning of basis state. And of course, I also have the freedom just say this is 3 spin up plus 2 spin down, if that is what I'm talking about, if we are referring to same basis. Is that okay? Okay, good. So with this, nothing, right? But what if I change my coordinate system to this? Instead of x hat, I call it x hat dash and y hat dash. But it has this system: 2, 4, 6, 8. For the same distance you see on this plane, I call 1 unit, now becomes 2. They all scale up by 2 times. So in this case, for exactly the same vector, v equals to the same vector v, how do I represent it as a combination of x hat and y hat? I mean, x dash and y dash. What is that? Let me ask again. So let's say I buy a dozen of eggs, right? That's in my book example. My mother asked me, how many eggs do you buy? I say 1. They say 1 what? 1 dozen. Okay? Or I can say 12. 12 what? 12 eggs. So now I have 2 different bases. One basis is 1 dozen. One basis is 1 egg, right? Are they the same? They are the same, right? Because 1 dozen equal to 12 eggs, right? So in this case, what is y hat? What is v? What is vector v in terms of x dash and y dash? In terms of the new coordinate or new basis? 6 what? Thank you. 6x hat dash plus 4y hat dash. Okay? Now, if I want to write in column form, it becomes 6, 4. If you compare this and this, they are the same vector, but I'm giving different number. However, I claim that they are the same. Is there a problem? You say no. Why? It is not a problem. 3 is not equal to 4. 2 is not equal to 4. 3 is not equal to 6. 2 is not equal to 4. Why is not a problem? Yeah.
Maybe the length of the division itself.
Thank you. Because the bases are different. So the length, total length are the same. Right? So when I say this is 6, I say I have 6 units of x hat dash. Right? And this is 4 units of y dash hat. Okay? Is this clear? I mean, this is very important. Also looks simple, right? But you don't want to get confused. Any questions regarding this? So if you just tell someone this is 3, 2 and this is also 6, 4, they don't understand. They say you make a mistake. But if you have the same protocol, you already tell that when I say 3, 2, I mean x hat, y hat. When I say 6, 4, I mean x dash and y dash. Then you don't have problem. Right? So similarly, I can write this as whatever I want, still 6 happy face, but not happy face. Maybe this time happy face dash. Because this happy face is different from that one. They have different meaning. Okay? So they have different bases. So now I have 2 bases, right? So 2 bases that I have shown you. One is the x hat, y hat. The second one is the x hat dash, y hat dash. If I represent in different bases, the representation will be different. 1D is very easy. You ask how tall I am, I say 160, let's say 170. 170, right? 170 feet? No, of course, it's 170 cm, right? Or I might say 5 feet 5 or whatever, right? So same height, different units. It is talking about the basis is different. Okay, so in the whole process of quantum computing is linear algebra. Whenever you do some computation, you need to make sure that which basis you are working on. If you mess up the basis, then all the results will be wrong. Okay, any questions? Okay, now fine. So now we go back to what we learned in linear algebra. What is the meaning of inner product? We just know how to represent a vector, so remember that. And let's just review the meaning of inner products, because inner products is a very important thing in physics and linear algebra. The important thing about inner product is that the inner product of two vectors will not change if you change the basis. Right? Just now I changed from cm to feet. My height looks like changed a lot from 150 to 150 to 15.5, right? But the inner product should not change. But we will learn that later. But let's review what is inner product, because from there we want to introduce some mathematical computation method. Okay, so let's again look at a coordinate system. X hat, Y hat. Now, I'm only working on 2D. Eventually, you find that the concept can be extended to many dimensions. So that's why we only work on 2D now. Now, I have a vector like this. I call this vector V1. Okay, and this is square root 3. And this is 1. I also have another vector here. This is 1. Okay, and this is called V2, vector 2. And if you forgot trigonometry, it doesn't matter, but just want to tell you that here is 30 degree and here is 15 degree, because 1 give me 45, right? So my pen has problem, it's difficult. This is 3, 0. Is this okay? Right? We forgot, doesn't matter, go back to review. Now take it for granted, 30 and 15. So what is the inner product of these two vectors by definition? Okay, so first let me write down what is V1. So let's take this as an example. What is V1 in terms of vector form? I mean in terms of X and Y. Square root of 3 plus 1y. Okay. Now other student, how about in column form? How do I write it? Square root 3, 1. Thank you. And again, I write it because we all agree the first one refer to X hat, the second one refer to Y hat. Okay. So how about V2? What is this? 1, 1. Thank you. 1 X hat plus 1 Y hat. Of course, some of you will say, why do you write 1? Actually, you don't need to if you think too much. And in column form is 1, 1. Okay. Now, first go back to our knowledge in trigonometry, or we learned earlier for real vector. We knew that V1 dot V2, which is the inner product of two vectors, is equal to the length of V1 times the length of V2 times cosine theta. And theta is the angle between them. Okay. So if you forgot, let me quickly just remind you. For example, if you have V1 here, this is a vector, and you have V2 here, this is the vector, and if this is theta, then V1 dot V2 is equal to the length of V1 plus times the length of V2 times cosine theta. Okay, take it for granted, right? If you forgot, otherwise you should remember. And it doesn't matter if you forgot, you just need to memorize it, put in your cheat sheet or whatever. Okay, this class is about quantum computing, not trigonometry. Is that okay? But you need to remember, okay? So but we should also review some of the basics, right? How do you find the length of V1 in a 2D plane? Yes. Square root, thank you, of what? X component square, Y component square. Very good, right? X component square plus Y component square, take the square root is the length, okay? Then how about that for V2? 1 square plus 1 square, because both are 1, right? Now, this is cosine 15. This is given 15 degree. Okay, so you are going to calculate yourself using calculator is 2.732, right? I use this because we want to compare later. This is not important, but you need to know, okay? So that is the inner product, okay? So actually, what is the meaning of inner product if you look at this? It basically say this, the inner product is like that. If I, in this figure, right, I draw a perpendicular line to here. This part is actually the length of V2. Anyone still remember trigonometry? What is the length of this part? V2 cosine theta. Okay? Because that is the definition of cosine theta, right? This one divided by length of this one equal to cosine theta. So the length of this one is V squared cosine theta, right? So now you see what is the meaning of inner product. The inner product of V1 and V2 is just the projection. So this is a key word, right? Later, we will keep talking about projection, but it will be at very high dimensional space. You cannot see it. But I hope that from this 2 dimension, you see what is the meaning projection. You just have a sunlight shining perpendicular to V1 and blocked by V2, and that is its shadow, right? Projection of V2 on V1, right? So V1 is like the 4, and I'm just standing with an angle, the sunlight shine above, and then my shadow is the projection, right? Projection of V1 on V2 on V1. Of course, we further multiply by V1, so it is scaled by V1, right? So it's scaled by the length of V1. Okay, but later you will find that we only deal with vector with unit length. So V1 and V2 modulus, which is these two, are both 1. Later you will see that we need that. Then in quantum computing, basically inner product is just the projection of one vector on another vector. Make sense? And now you may understand why inner product doesn't change under unitary transformation. The transformation I gave you earlier is not unitary, but we'll talk about that later. But basically, the relationship between two vectors does not change, whether you look from this angle or from the other angle. Okay. Okay, any questions about this typical way, traditional way of calculating inner product? Basically, it's just V1 times V2 modulus cosine theta, right? We just review this, okay? Now, then we have this, what do you call? This column form, right? There's another method to calculate. Let me call it method 2. We don't need trigonometry. So let me remind you, we say V1 equals to square root 3, 1. V2 equals to 1, 1, okay? And then the operation is like this. We will learn that. You may learn that before, but let's learn it from scratch. Something called transpose. Anyone know what is the transpose of V1? What does it mean? Anyone still remember from your previous? Yeah, look at his hand. It rotates it by 90 degrees. Okay? Transpose means column becomes row, row becomes column. Okay? So yeah, like what he's doing, I visually will think it as this is a column. I rotate it 90 degrees to the left or anti-clockwise. And that is what it means. Transpose of V1 is now becomes this and then square root 3, 1. Do you see that? 90 degree anti-clockwise. Okay, so a column vector becomes a row vector, right? So this is called row vector. It's just a way of writing things, but it has a lot of important, not row. So the transpose of V1 is square root 3, 1, okay? This is a real system. So I'm not going to talk about complex number yet, but a more general form is not this. But for now, let's just understand this is a transpose. Then what is then? V1, and I actually need to give it a name. I just call it V1 transpose, okay? T here. T on the top right as mean is transpose. So V1 dot V2 turn out to be V1, I should not write this. Turn out to be, I just write down square root 3, 1, but transpose on 1, 1. Okay, do you understand what I'm talking about here? So this is dot V1, dot V1 dot V2. It means the inner product of V1 and V2. And I say that it is the column vector transpose of V1 times the column vector of V2. Let me write out the result, then it will be easier to understand. I take the transpose, it becomes square root 3, 1 times 1, 1. Okay? Now, do you still remember how to do matrix multiplication? Some of you might forgot, right? So I have matrix, I have two matrix. What do? I multiply this row with this column. Then I get the first element, right? So if you forgot, we will try to show you slowly in the future. But for now, again, take it for granted. How do we do the multiplication of this one? Again, this row, this is a row, times this column. So exactly what will we do? We first will do square root 3 times 1. This row times this, right? So this 1 times this. Square root 3 times this, okay? Plus this 1 times this. 1 times 1. Are you okay with this? Row times column. You multiply the corresponding, actually it's an inner product, right? You multiply the corresponding element. This first one times this one, plus the second one times the second one. Then you get this one. If you go through the math, this gives you 2.732. Same as before. 2.732. Here, just to say that the equation we have been using is the same as this one. So now you see that if you're 2D, I can talk about cosine theta. What is 100 dimension? There's no such thing, right? So this is a more general definition of inner product. What we learn in high school or undergraduate are special cases in 3D. But it is a more general one is that if you write it in column form, again, what is column form? Each element represents the components of basis. And then you go through this matrix multiplication, you get the same inner product. Okay, but here I need to warn you a very important thing, and this is the case in quantum computing. It will always be the case. This method works only when the basis is orthonormal. We will talk about this later. Okay, what is the basis state here? Basis vector here. Can someone tell me? What are the basis vector? Good. He said X and Y. Do you agree? Anyone disagree or don't understand why? Right, so when we start working on column form, we forgot the basis. We will suddenly forget, oh, which basis are we working on? Then you need to remind yourself, right? So here, we just write down the component amount. We did not say what are the basis vector. And this only work when the basis is orthonormal. What does it mean? It means that, for example, the basis are what? X hat and Y hat, right? It means X hat inner product with X hat equal to 1. Y hat inner product with Y hat equal to 1. But X hat inner product with Y hat equal to 0. Now, let's go back. Now, if you look at this, I hope that you will start appreciate. What is the inner product again we said earlier? It is the projection of a vector onto another vector. So if I say x dot y equal to 0, what does it mean? Zero projection, right? How can you have zero projection? You are perpendicular to it. Very good, right? So in our real 3D space, we understand the meaning of perpendicular. But if I have a 10-dimensional space, I said that vector is perpendicular to another vector. You cannot understand. But from here, you see that as long as their inner product is 0, then they are perpendicular. That is the meaning. Okay? So we'll keep talking about this, right? And here, x hat dot hat equal to 1, y hat dot hat equal to 1 means that they have unit length, right? Because you project to yourself, you actually, if you remember this equation, it is talking about the square of your length. The square of your length is 1. It means your length must be 1, right? We cannot have negative length. We cannot have imaginary length, right? So that's why it's called orthonormal. It's orthogonal for different bases. They perpendicular to each other, and it's normalized for each basis. They have a unit of 1. And of course, that is what we have been dealing with, right? In 3D and 2D spaces. Okay, so this looks simple. I hope that it's possible. Some of you will say, oh, after going all this math, you're telling me something very trivial. I already know. It's true, but my purpose is to link some new definition to your daily life, right? So now when you do inner products, no more thinking about this equation. Of course, you can use it to help you to understand. But now inner product is actually means transpose of one of them times another. But they have the same, and what is the meaning of orthogonal and normalized? Okay, any questions? Okay, so all this needs some practice, and if so easy, then we can go to a higher dimension because we really don't need to visualize it. We kind of persuade ourselves what we have used, right? The column form, inner product, definition of perpendicular normalization, correct. They match to our daily life definition in 2D and 3D plane, right? Like the projection is 0. So I can easily just go to higher dimension. And why? Because think about this. If there's a kind of animal, a civilization like ants, let's say the ants, a new civilization, and they can only walk on a 2D plane. They cannot understand what is the meaning of 3D space. But when they talk to you, you will try to explain to them what's the meaning of 3D space, right? And they still cannot understand, but they can understand by doing analogy to their 2D space. So now we live in a 3D space. You cannot understand 4D, 5D, 6D, right? But based on your understanding in 2D and 3D, you can extrapolate your experience and understand and accept what will happen in the higher dimensional space. Okay, so let's see if that is the case. So now, let's say I have a high dimensional space. This is ND, n dimensional, right? N can be from 1 to 1 trillion or any integer, right? So I have two vector VA. How do I write it? I actually should also say that it's n-dimensional and its bases are V0 hat, V1 hat, V2 hat, all the way to Vn minus 1 hat. I tell you that this is given. The basis states, I call them V0 hat, V1 hat, V2 hat, all the way to Vn minus 1 hat. And if you feel confused, then you just step down. Let's say n is 3. Oh, then I have V0, V1, and V2. And in 3D case, well, this is just like X hat, Y hat, Z hat for 3D, right? So if you're okay with 3D, calling X hat equal to V0 hat, Y equal to V1 hat, Z equal to V2 hat, then you have ND, you just continue to have more. Make sense? Right? So I tell you there's a space, n-dimensional, right? You cannot feel it, you cannot imagine it, but okay, I have n-dimensional, right? So if that is the case, any vector in this space, right? Any vector, and let me call it VA hat, A, right? Equals to A0 V0 hat plus A1 V1 hat plus A2 V2 hat all the way to AN minus 1 VN minus 1 hat. Is this okay? In 3D, I can say it is A0 X hat plus A2 A1 Y hat plus A3 Z hat. Done. Any vector in 3D. Now it's in ND. Then I will just have n coefficient. Make sense? Can I write this in column form? What would it look like?
081.
A0, A1. Thank you. AN minus 1. Again, when I write this, then I did not say the basis, but we need to agree with each other when you're doing the problem. We agree with each other. Okay, it means I have A0 parts of V hat, A1 parts of V1, right? A2 part of V2, and AN part of AN minus, VN minus 1 hat. Right? So we did not learn anything new. We just expand the dimension naturally. Okay? Now I also may have another vector VB hat equals to B0 V0 hat plus B1 V1 hat plus B2 V2 hat all the way to Bn minus 1 Vn minus 1 hat. Make sense? Are you okay with how I write it? Okay, and then what is the inner product between of them? I just define. This is just a definition. So do not worry. The mathematician already fight for hundreds of years and find that this one makes sense. The definition of A dot B, VA dot VB equals to A0 star B0 plus A1 star B1 plus A2 star B2 all the way to AN minus 1 star BN minus 1. Now you get confused, right? But let me write in a compact form first. This equal to summation. I call it I equal to 0 to N minus 1 AI star BI. So first of all, let's review. What is the meaning of star? Anyone know what is the meaning of star? A star, what does it mean? Thank you. It's the complex conjugate of A. But what is complex conjugate?
Wherever you see an I, minus.
Yes, when you see an I, put a minus in front of it, right? For E student, you should be very familiar with this because when you deal with the AC phase signal, right, you always use complex conjugate. And for physics student, maybe they use, I actually forgot whether physics use J or I, right? So we sometimes don't talk to each other. But for example, if I number 2 plus 3I, okay, let's say A equals to 2 plus 3I. Then what is A star? 2 minus 3I, thank you. Right? The imaginary part becomes 0. Okay, so this is a basic thing. If you forgot, you really need to pick up, right? This is a very basic. Any questions? So what does it tell us? It says that, hey, you see, I have VA. The VA, of course, is a superposition, linear combination of the basis state. And by how much? A0, A1, A2, right? So A0 to AN define VA. It's not V0, V1 define VA. Because V0 to Vn minus 1 are the basis state in the state. Everyone share the same basis state. Right? You are taller than me, not because you use feet. We all use feet. The reason you're taller than me is because you're 6 feet and 5 feet, 5.5 feet, for example. Right? So you all have the same. So what defines us is the number in front of the basis state. And same for B. So the inner product between A and B is what? It says that you just multiply their coefficient together and add them together. But the first one, you need to take the complex conjugate. So A0 complex conjugate times B plus A1 complex conjugate times B1 plus A2 complex conjugate times B2 plus AN minus 1 complex conjugate times BN minus 1. Right? You just multiply the coefficient together and sum them together. Now, do you remember we have done this already? Isn't this was what we did? This is A0, this is A1. This is B0, this is B1. And exactly is A0 times B0 plus A1 times B1. Except this is just two-dimensional. And also, we don't have complex conjugate, but I did not do anything wrong because they are all real number. The complex conjugate of a real number is itself. It doesn't change, right? So I'm okay for my definition here. But a more general definition should have the complex conjugate. Okay, so this is the equation you need to memorize. Okay. Okay, then, any questions? Yeah, so let's continue, right? So let's put in column form. Although I already wrote one of them earlier. And try to see why I want to put in column form. In in column form, I have VA equals to A0, A1, AN minus 1, right? That's what I did here. A0 all the way AN minus 1. Because I put the coefficient, I stat the coefficient, right? How about B? What is VB? Someone tell me. B0, B1, Bn minus 1. Thank you, right? So let's find what is VA dot VB. Based on the previous equation, it actually, this is just equals to A0, A1, AN minus 1, the whole column. You take complex conjugate and transpose, and then times B0 B1 to Bn minus 1. Okay? How? This become what when you do the transpose, what do you get? Row column. Row vector. And this is A0, A1, AN minus 1, right? I still miss one thing. Besides transpose, what else do I need to put? Complex conjugate, right? You put the star there. Any question from other students? Right? And then this whole thing times B0 to Bn minus 1. And again, what do? You just do the vector matrix multiplication. This row times this column. And how do you do that? The first element times the first element plus second times second, right? So this is just A0 star B0 plus A1 star B1 plus all the way to AN minus 1 star Bn minus 1, which is just what we said earlier. I equals 0 to n minus 1 AI star times BI, the same as before. Okay, so now we finally established the real definition that we are going to use in this class when we do inner product. You get a vector form, transpose the first one, applies complex conjugate, and then do the matrix multiplication. You need to follow the step clearly, right? Don't miss any of them. Okay, any questions? Okay, so it's good you understand everything. But the worst case, you need to know how to do the inner product of these two vectors. That is a must. Okay? And why we have this, the best is you really understand, you can connect to your real life experience. That would be the best. Okay? Now let's go back to talk about orthonormal basis. And we need this in quantum computing. Okay? So first of all, let's recall what is basis, right? We have many different basis systems. We used it before. For example, what do we have? We have X hat, Y hat, Z hat. These are the three basis states for our real 3D space. Any vector in this space is a linear combination of the basis state. Right? I'm repeating, right? But you need to understand. So if you agree this is the basis, this is okay, right? This is the basis vector. If you feel comfortable to describe your 3D space like this, you should also feel comfortable if I tell you this is a space with the spin up and spin down as the basis state. Right? Because the ends also upset us to tell them that Z hat is also a basis state. The ends doesn't understand what is Z. Right? Of course, n can go up, but let's say a new type of creature, right? They agree, yeah, okay, Z hat is a basis state. Now I tell you that there's another space which is spin up and spin down. You should also agree, right? Because the new creature agree that Z hat. Okay? But this space doesn't mean there is something, someone live there. I don't know actually, right? But it's a space. Okay? Or you may have n-dimensional space. For example, you have A0 hat that we just learned, AN minus 1 hat. This is ND space, right? Okay? So now what is the meaning of an orthonormal basis? We actually gave you an example already, but now we will do a more general definition of orthonormal basis. It means AI hat dot AJ hat equals to 0 if I not equal to J, equals to 1 if, what happened to my computer? I equals to J. Okay? What does it mean? Let's look at this three n-dimensional space. Aij. So the subscript tell me which basis vector. So if I not equal to J means that you are doing an inner product of two different bases. Then you get 0. And this is the so-called orthogonal condition. Right? They orthogonal to each other. But if I equal to J, meaning you are doing the same inner product yourself, A0 dot A0 or A10 dot A10. It is 1, then it means the vector are normalized, which I just told you earlier. And that's why it's called orthonormal, right? Orthonormal. So this basis is an orthonormal basis. For the space we're going to do quantum computing need to be orthonormal. You will understand later why. Okay? So let's make an example, right? Which you already know, but let's still do a simple example. For example, in a real 2D space, right? We have x hat dot x hat equal to y hat dot y hat equal to 1. X hat dot y hat equal to 0. Now, can you tell me, if I want to represent in a column form, how do I write x hat? 1, 0, very good. 1, 0, right? Where some of you might suddenly get confused because it has 1 unit of x hat and 0 units of y hat. Okay, how do you write y hat? 0, 1, thank you. Yeah? So we can do a simple check, right? X hat dot y hat, how do you compute? You need to transpose, thank you, of x hat, 1, 0, and then multiply by 0, 1, which is equals to 1 times 0 plus 0 times 1. I deliberately write it in order, so I hope you can follow, make sure that you don't do the multiplication wrong, right? So they are normal to each other. Orthogonal to each other. Any questions? Okay, so we learn what is a vector, how it is represented in the basis. The most important is what is basis, what are the basis vector, and we learn inner product. From there, we know that there's a space called orthonormal. I mean, there are a type of basis. They are called orthonormal. They are very important. You will see later, but we will use it in quantum computing. Okay. Then let's move forward to learn some more stuff. Now I want to talk about the bracket notation. Okay, we have been using it, right? But we just want to talk more, right? So cat, what is that? It's actually just a vector. We have been representing it as VA arrow, right? So when your teacher told you that a vector is written with an arrow on top, anyone has challenged him or her? Why you write this ugly symbol? No, right? So if you did not challenge your teacher, you should not challenge me if I write it in this way, right? That's first of all, right? So, but this way has a very useful, it makes things very handy and simple in the future. And the way we write it follow the computation rule very well. So now you all a promoter to a physicist, right? They use this 1-to-2 series computation. So this is called cat. So cat is nothing but just a representation of vector, right? So it's just a vector. So if that is the case, I can call it A also, if we already agreed that A means vector A. Okay, so I can put anything there, right? For example, I can even say this polarization if I want. Because we all agree that this is a vector, right? It doesn't matter what I write inside. I cannot use it, I cannot do multiplication or any operation inside the cat because it's just a language, a symbol. Okay, so that is cat. It's nothing special. You already learned what is cat. It's just a representation of vector, right? So you also learn vector addition. VC equals to VA plus VB. When you do this, you actually don't touch this symbol. This is just a symbol, right? So I can also write it as what? VC equals to VA plus VB in the cat's form. Because you know that this is just a vector. And because we don't care what is written inside, as long as there's no confusion, I can as well think that this is C equals to A plus B. They represent the same thing. The point is that we all agree that they represent the same thing, so I can write it in this way. Right? So you can use, I don't know, right? Let's say Greek letter, Russian, German, the corresponding alphabet. If you agree, it's still the same. We're talking about the same math, same physics. Okay, so this is cat. And of course, you may say, okay, now what if I have a number A times VA? So what is A when you see this? Is this a scalar, vector, or matrix? Scalar, right? So it can be complex, maybe I, but it's a scalar. It's just a number. And you know this is a vector, right? So if you can scale a vector, then I can also scale it if I write it in this form. So I have a number in front of cat. Although it looks weird, but it's just a vector. Just remind yourself, it's a vector. I can write whatever I want, but don't touch it. Don't break it. Don't try to do operation inside, okay? But I can change the meaning. I can write English, write Chinese, write Japanese if I really want, as long as we agree with each other. Okay, so K is nothing, right? So it looks like it's very simple. You just change the vector form to this notation. Any questions? Okay, now then there is another thing more interesting. It's not more interesting, but when you combine with cat, it becomes very interesting. We talk about bra. So what does it mean? So bra, let's just take it for granted, it's a dual vector space. So first of all, maybe I did not emphasize enough. We are talking about vector space, right? We have a basis, we have basis vector, and then inside this space, every vector is a linear combination or a superposition of the basis state. So that form a vector space. For example, 3D, every point in this room is a vector, right, to the origin. And this is a vector space. Now, bra is what? It's a dual vector space of the cat space. Okay, so it's just, you can think it as a mirror image of, so if I'm a vector, right, it's not exact mirror image, however, just thinking that if I am a vector, I stand in front of the mirror, My image inside is my bra version. And all those images, so every one of us is a vector. We form the vector space. And then our images in the mirror becomes a dual vector space, is a bra space. Right? So a little bit difficult to understand now, but let's just look at the operation first. For example, this is bra A. Okay, this is the bra of A. Remember, I told you that A in cat is a vector. This is also a vector, but this is the dual version. Just imagine it's the image of A, something like that, right? So we say this is the bra of A. Writing this is not easy to see, right? But exactly what it is, it's the transpose and complex conjugate of A. So what does it mean? For example, if A, again, A is a vector, right? I write it one more time, the last time I write in this form, VA, the last time. If it is A1, A2, A3, first of all, can you tell me how many dimensions? Three dimensions. But it's not necessarily real space, okay? If this is A, then what is A bra? Row vector, thank you, because it's a transpose, okay? So it becomes A1, A2, A3, and also complex conjugate. This is just the definition. Take it for granted, definition. Okay? So when I give you a vector, you can write in the in the column form. Then its bra version is just the transpose complex conjugate. Okay, so you just rotate it anti-clockwise 90 degrees and add the complex conjugate to it. That is the bra of A. Now, do you recall something? When did we just see this? What did we do when we do this rotation? Inner product. When we define the inner product, we say that the inner product of two vectors is just computed in this way, right? Then what does it mean? Then it means the inner product of VA and VB, but now we write it as A cat and B, right? Is the bra of A times the cat of B. Maybe I'm too fast, right? How about I say this? Is A star 1, A2 star, A3 star times B1, B2, B3. That is the definition of inner product, right? Remember? Rotate, complex conjugate, transpose times the vector, right? But what exactly is this? This is just A bra times B cat. Because I already tell you that, you just take it for granted. Bra is just the transpose and complex conjugate of cat. Now we can write it in a more succinct form. We don't need to put them as two vertical bar. We can combine them. It doesn't matter. You can keep them, but this is better. And that is the inner product. And now with bra, and now you probably understand why this is called bra or cat, right? Because this is a bracket. So bra and cat. So the whole notation is always that you see a lot of bracket. Okay? That's what I want to say. So how to do this? You don't need to worry too much. For those who really want to go deep, you can go to the math, take a deeper look on the bra. But that's like, mathematician come up with this dual space, right? It's a pretty complicated concept, but they are still vector. But the point is that every vector should have their dual version. Do not forget, although we keep saying that bra is the transpose and complex conjugate of cat, but cat is also the transpose and complex conjugate of bra, because when you take a transpose and complex conjugate of this one, you will get back the cat version, right? Because this two complex conjugate will be gone, right? And then you transpose it back. Okay, so they're dual image of each other. So you think that you're looking at mirror, maybe the mirror actually have a living there. They are looking at you as an image. You don't know, right? A little bit scary. Okay, but the point is, I hope you get used to this notation. Okay, when you see this notation, when it's cat, you know, oh, nothing, just a vector. It won't scare me. And then when you see bra, maybe a little bit confusing, but just remind us, it's just the transpose and complex conjugate of B. It's the dual space of cat. Okay. So at this stage, then we will go to another things, which is the vector state and superposition. Okay. This is pretty short, but this is something very important, okay? Why we talk about vector? We're talking about quantum computing. Why we care about vector space? That is because in physics, every state, okay, every physical state of a physical system is a vector. Do not underestimate the importance of this. For example, I'm running at 5 meters per second, 1 meter per second, cannot be so fast, 1 meter per second. That is my physical state. And that is a vector, okay? And this vector is a linear combination of some basis state, the velocity in 3 dimensions, right? Think about that, right? So every physical system, it has a state. And actually, your purpose is to find out which state it is in, because every state have a corresponding property, okay? So every state of a physical system is a vector, and that's why we study vector, right? And we already see that every vector is a superposition. What is superposition? It's just linear combination. Okay. Superposition is a fancy term when people talk about quantum computing, but it's just linear combination of what? It's a linear combination of what? Every vector. So for example, thank you, of the basis state. Okay. So if we agree with this, then now I hope that you understand a general spin state. I did not talk about spin, but you don't need to understand what spin is. You just need to accept that, yeah, there may be a space is for spin. So as general spin state, you don't even need to know how to read it, because I know this is a vector. Now you write in Greek. I don't want to write in Chinese or Japanese or English. It's my choice, right? I just know it's a general state. It's what? It's a linear combination of its basis states, but we know that the spin only have two, or it is given two basis states, spin up or spin down. Right? So at this moment, I hope that you won't feel uncomfortable with this expression. First of all, everything in cat is just a vector. And what is a vector? Well, it's not doesn't need to be 3D now. We know that, right? It's just to describe the state of a physical system. And it must be a linear combination of the basis states because the spin space is formed by these two basis states, spin up and spin down. So alpha and beta are just scalar coefficients, right? So because of that, I also can write this as alpha beta. But what is alpha now? It represents spin up. It doesn't represent x hat. Okay? And this is spin down. It doesn't represent y hat. Right? So you might have, although we need to normalize, but let's say continue to use 3 and 2. Right? Although it's 3, 2. And the 2D case, we also have 3, 2 in the 2D space. But they are different vector. They represent different things completely. Because the basis state here is up and down. The basis state there earlier was x hat and y hat. Okay? And that's why it's very important to pay attention to the basis state. Okay? Any questions? Okay, so remember our goal is to understand the states of a physical system. And they can all represented by the vector space, by a vector. And this vector must belong to a vector space. Okay, and it depends on the problem we are talking about. It can be as simple as how fast this particle is moving. Then that vector space is just the velocity in 3 dimensions. Or what is the spin of this particle? Now we're talking about vector space we cannot see, spin up and spin down. And it can be a linear combination of spin up and spin down. Okay. Oh, so this is the last slide. Okay. So now we know what is a superposition, right? So then it means that for a general state, right, in n dimension, it doesn't matter this is a what type of space, ND, right? I have a vector which is V equals to A0 V0 plus A1 V1 plus AN minus 1 Vn minus 1. Is this okay? What are the basis states? V0, V1. Yeah, thank you. I still put them in cap because they are vector. Basis states are vector. They are states, so they are vector, right? I'm lazy. I try to write in this way. Instead of V1, I just call it 1. Would that be a problem? No, because everyone in CAT is just a description of the basis state, right? I can even say ZERO, ONE, TWO, right? 1, 2, 3, 4. I can spell them. Because they are representing the basis state. This is just a vector. It's just as simple as when your teacher told you this is, let's say this is vector A. No. How to say? Vector V0. I don't know, maybe in your class there are some smart student or naughty student, they deliberately write it as V0. Right? They are correct, right? The teacher cannot take score out from them, right? So that is exactly what we are doing here. Okay? So, okay, this is a general space. So in the column form, it will be A0, A1, all the way to AN minus 1. I did not introduce anything new, right? Except that I changed to the cat notation. Okay, so now we have this coefficient. What I want to say is, what happened if we do a measurement? Do you remember? This is actually not much to new thing to learn. What happened when you do measurement to this state? Thank you. Measurement, it will collapse. Collapse to what? Thank you. Collapse to one of the basis states. collapse to one of the basis states. So for example, but how? Is it deterministic?
No.
Randomly. But with a probability, right? Of AI squared for let's say I state, right? I'm using 0 to n minus 1, right? So it collapses to I, for example, collapse to 1 with A1 square, with this probability, okay? And that's it. We will do some calculation, but let's just understand what is AI squared. You need to memorize this equation. Also, you're supposed to know this already. AI squared is also equal to AI star times AI. Okay, so let's try two methods. Okay, so how about let's say assume AI equals to 1 plus I divided by 2. So this is a problem. I actually should not have this example because it's not normalized. Oh no, it's okay because I did not say what it is. Okay, let's say AI is 1 plus I over 2, okay? What is AI star? Thank you. 1 minus I over 2. Again, the imaginary part is negated, right? So what is, if you just calculate it based on what you learn in complex number, the length is just the square root of 1 over 2 square plus 1 over 2 square, the whole thing square. So what I'm doing is that square is here, right? The length of this complex, or the modulus of complex number, is the square of individual component. 1 over 2 square plus 1 over 2 square, and then take the square root. Right? So what is this? This is equals to 1 over 4, 1 over 4, then 1 over square root 1 over 2, then the whole thing square equals to 1 over 2. Right? So I have 50% of chance collapse to AI if AI equal to this. Okay? Now another method is I just use AI star times AI, right? You know they are the same, but we just practice. AI star is 1 minus I divided by 2, and AI is 1 plus I divided by 2. So the denominator is 4. The top 1 minus I becomes 1. Maybe I just go through that. You actually should know that A minus B times A plus B equal to what? But let me just multiply, right? So it is 1 times 1 minus I times 1 plus 1 times I minus I times I. What is I times I? Minus 1, right? So you have 2 minus, right? So it becomes plus 1. These two get cancelled. So this again equal to 2 over 4 equal to 1 over 2. So, I mean, you need to make sure you know how to do this calculation. You don't waste time on this, right? Because you are going to do something more important. Here just to show you that they are the same. Okay, so time's up. Let me know if you have any questions.